Hello, my name is Beth Dixon, and this is a video series based on Vicki Borlaug's PowerPoint presentation on proportions. Ooh, I got click happy. Note this is designed to be viewed after confidence intervals and hypothesis testing on the mean as we talk about those things for proportions. I wish to thank Mrs. Borlaug for allowing me to use her PowerPoint to make this set of videos. And this is part 5 of the series. In part 1, we talked about an introduction to proportion. In part 2, we talked about whether or how to determine whether a binomial can be approximated by a normal distribution. In part 3, we talked about confidence intervals for proportion. In part 4, we talked about sample size for proportions, and now in part 5 we are ready to learn how to do hypothesis testing for proportions. So let's jump right in to example number 4. A florist randomly selects 224 weddings that they had done. 217 of the brides want to have roses in their bouquet. Using a 0.01 level of significance, test the claim that more than 95% of brides want roses in their bouquet. Notice that we know that this is a hypothesis test when it says test the claim. We know it's not a confidence interval. It says nothing about confidence intervals. It's not a sample size because it doesn't say how many or how large a sample. It is a hypothesis test. We know it's not on the mean because it doesn't say anything about the mean. It says test the claim that, and then it says more than 95%. This means that the claim is on the proportion is more than, and we need to change the 95% to a decimal of 0.95. We need to change it to that decimal, and then we're ready to proceed. Here's our problem again, and the first thing we want to do is talk about the steps we'll complete. Step 1 will be to find x, n, p hat, and q hat. Those are our vital statistics. Step 2 will be to check to see if the binomial can be approximated by a normal distribution. And to do so, we will check n times p is greater than or equal to 5 and n times q greater than or equal to 5. Please remember that some teachers will use n times p times q is greater than or equal to 10. It's still the same step regardless of which formula you will use here. Step number 3 is to use hypothesis testing to test the claim. And the hypothesis test statistic that we will use in the hypothesis testing is z equals p hat minus p all over the square root of p times q over n. Step number 1, find the x, n, p hat, and q hat. Let's refresh what each of these will mean specifically in our problem. X will be the number of successes, or in our case, the number with roses. N is our sample size, or the total number sampled of brides. P hat is the estimate of proportion, in our case, with roses, and Q hat will be 1 minus P hat, or the estimate of proportion without roses. So the number with roses is 217. The total number sampled, 224. So how do we estimate the proportion with roses? That would be the 217 out of the total of 224. Divide that and round to 3 decimal places, 0.969. Remember to follow your teacher's rounding rules. Q hat then will be 1 minus 0.969, which will give us 0.031. Let's write those 3 or 4 variables, and we'll place those in the box here to the left, and we're ready to proceed to step number 2, and we will check to see if the binomial can be approximated by a normal distribution. To do so, we'll check by doing n times p greater than or equal to 5 and n times q greater than or equal to 5. Since we don't know p or q, we will use p hat and q hat as estimates here. So n times p hat gives us 224 times 0.969, which is 217.1. That is greater than or equal to 5, and we'll place a check mark. 224 times 0.31 for n times q hat gives us 6.9. That is also greater than or equal to 5. So check, we're ready for the second one. Since both are greater than or equal to 5, we're ready to proceed to step number 3. Again, our vital statistics there, and our alpha, and you can go back and read the problem to verify that, is 0.01, and we're testing the claim that the proportion is greater than 0.95. Now we're ready to proceed with the hypothesis testing. Remember that we could use the classical approach or the p-value approach depending on what the directions are for the particular problem. For this example, we will use the classical approach and Mrs. Borlaug's 5 steps. Remember, Mrs. Borlaug has this particular structure that she uses in the 5 boxes to help you to remember the 5 steps: hypotheses, critical value, test statistics, conclusion, and the sentence in terms of H1. The hypotheses. To get the hypotheses, we will need the null hypothesis and the alternate hypothesis. So, to get that, we will read the claim again. The claim is that the proportion is greater than 0.95. Greater than does not contain a condition of equality, therefore it goes in the alternate hypothesis, and that will be p is greater than 0.95. We use p here because we're talking about the proportion, and we are not talking about a mean. So since we're not talking about a mean, we do not use the symbol mu. Mu means mean, p means proportion. So this is p greater than 0.95. To get the null hypothesis, remember that the symbol for greater than for the null will need to be the opposite, which will be less than or equal to. And again, some teachers will just include this as equal to, but it will still be proportion, less than or equal to 0.95, and that gives us our hypotheses. We are ready for the critical value, which we always start with our normal curve. All proportions are z values, so this will be a z critical value. I went too far. So with your z value, you will go to your table and look up 0.01. And since it is greater than, that will be a right-tailed test. And using a one-tailed test and 0.01, you will go to the bottom of your chart and find that your z value is 2.326. And that gives you the right-tailed test with the area in one tail of 0.01. That gives us the reject region to the right and the do not reject region to the left. We are now ready to do the test statistic. Remember, your formula for the test statistic is z equals p hat minus p all over the square root of p times q over n. That gives us p hat at 0.969 minus p, which is the 0.95, all over the square root of 0.95 times 0.05 all over 224. Now notice to write this how easy it is and how much better it looks with parentheses under the square root. If you put the parentheses under the square root in your calculator, especially the older versions of the TI-83 and TI-84 calculators, you may get the wrong answer by prematurely ending the square root before you need to. So it is best not to use the parentheses under the square root and just to use a times symbol, even though it will look better on your paper to use the parentheses. Also remember to use parentheses around the top, or to enter the top, press enter, then hit the divide and press the bottom of your fraction. In either case, the answer should be 1.305. And if you're struggling getting that out of your calculator, please feel free to stop by the math lab here in MBSS 222 and ask for some help in getting this in your calculator correctly. Now, once you've got 1.305, place that on your normal curve and you will see that it falls to the left of our shaded region in the do not reject region. It is not unusual. It is usual. It's normal. It's ordinary. It is not unusual. Because it is not unusual, we do not reject HO. And then our sentence becomes, using a 0.01 level of significance, there is not evidence to say that the proportion of brides that want roses is greater than 0.95. Here is a class activity for you to try. And here are some of the intermediate answers to make sure that you're on track. As always, Walter State students are welcome to come by the Math Lab in MBSS 222 for any additional help, whether it's with your calculator, formulas that may be different that your teacher's using than what we've used or talked about. Any help that we'll be glad to help you with. As always, thank you for watching and have a good day.